In this video, we discuss Fourier cosine series. We will start with a review of finding the coefficients for a full Fourier series expansion of a function f. And then we'll talk about how those formulas for the coefficients simplify when f is an even function, or when the periodic extension of f is extended in such a way that it's even. And then we will construct a Fourier cosine series for a particular function. Now, this is from section 2.3 of Solution Techniques for Elementary Partial Differential Equations, second edition by Christian Constanda. So as a review, we start with some function f, defined on the interval from negative L to L. And we construct its periodic extension on R, but basically just drawing that graph over and over and over again to the left and right of the original graph. Because this was originally defined on a period of length, or on an interval of length 2L, this new function, this periodic extension, will have a period of 2L. So then at that point, it makes sense to talk about constructing an infinite series like this to represent that function. Now, sometimes these are equal and sometimes they're not. We talked about when this infinite series would converge to this function f in the last two videos. So I'm not going to focus too much on convergence here. But let's say we're trying to find a sub 0, a sub n, and b sub n. So those are coefficients that we're trying to find. And the way we found those in the first two videos was pretty straightforward. First, we said we have all of these identities that hold. We have these 5 identities. The integral from negative L to L of cosine of n pi x over L happens to be 0. And the same is true for the corresponding sine function. We discussed why that would be true, or provided some geometric intuition for why that is true in the first video. Then we said, if you take a sine function and a cosine function and you multiply them together, these two sine and cosine functions, and you integrate over the interval from negative L to L, you always get 0. Now, if you have two cosine functions here, it's going to be 0 most of the time. But if the angles are the same, so if the frequency of this cosine function is the same as the frequency of that cosine function, it turns out that you would get L from this. If you want, you can verify this identity, or really any of these, but you can verify this identity, and this identity using the methods of trigonometric integrals, which are usually in a calculus book. If it's covered in your calculus series at your institution, it's usually covered in calculus 2. So we see if you've got a cosine and a sine, that integral is 0. If you've got two cosine functions, you get 0 most of the time, except for when you get L, and that's when the angles are the same, or the frequency of both of those cosine functions are the same. And then the same is true here. If you have two sine functions, you're going to get 0 for this integral most of the time, except for when the angles are the same. And in that case, the value of the integral is L. So we said before, if you want to find a sub 0 or a naught, all you have to do is take each of these expressions, this one, this one, this one, and this one, and integrate from negative L to L. So we've got the integral from negative L to L of f equals the integral of this constant term from negative L to L. And then we have an integral of an infinite sum. Now, the integral of the sum is the sum of the integrals. So you can pull that integral inside and pull out that constant a sub n. It's going to be constant for different values of n. And then you focus on this over here. And we just integrate from negative L to L this cosine of n pi x over L. And we do the same thing with our b sub n. That part of the series, the integral of the sum is the sum of the integrals. So you can pull that integral operator inside. And we've got the integral from negative L to L of this guy. Well, because of our identities, which we discussed earlier, this piece is 0 and this piece is 0. And if we do a little bit of just calculus 1 integration here, we've got the integral of 1/2 a naught with respect to x over this interval from negative L to L. If we do all of that, it turns out we're going to get 1/2 a naught times x evaluated at L and negative L, and then you subtract, you're going to end up with 1/2 a naught times 2L. So you'll have a naught times L equals the integral from negative L to L of f of x. And if we divide both sides by L, we get this. So we're taking advantage of the fact that these identities hold. Now, if we have this equation and we're trying to find the a sub n's, if I'm looking at these identities, notice the a sub n's are multiplied by this cosine of n pi x over L. If I want to keep some of those, well, I think I need to multiply by a cosine of m pi x over L. So I'll have a cosine times a cosine, and that'll be 0 most of the time, except for when n equals m, and we'll get L. So that's exactly what we need right here. So in order to find the a sub n's, we will multiply this entire equation by cosine of m pi x over L, and then we integrate from negative L to L. The left-hand side was f of x, so we multiply and integrate. Then we have that equal to that 1/2 a naught. We multiply and integrate. Plus the sum as n goes from 1 to infinity of a sub n times this. Again, the cosine functions, we take those cosines, we multiply by another cosine, we multiply and integrate. And then the same is true with the last one. We had the sum as n goes from 1 to infinity of b sub n times these sine functions, multiply by the cosine, and then integrate. Now, because you've got a cosine times a sine here, this guy is 0. And over here, that's just a constant times this integral. Well, that was also 0. This is something that we can evaluate because we'll know what f is. And then this guy, well, it's got the 2 cosine functions in it. That's going to give us 0 most of the time, except for when n is equal to m. This is the sum as n goes from 1 to infinity. You can think of this as having infinitely many terms. Only one of those will be non-zero, the one where n and m are equal to each other. So this will be equal to 0 when n and m are different. And then when n is equal to m, so just picking off one number from that list, that integral will be equal to L. So in that way, we have this f times cosine, that integral of that is equal to 0 plus a sub m times L plus 0. So this is 0, and we end up with that a sub m times L from here, and that's equal to this guy. So from there, we can say a sub n, I'm just changing from n back to, or m back to n, is 1 over L times the integral from negative L to L of f of x times cosine of n pi x over L. That's because I've changed the m to m here and there. All right, now the last thing that we do in order to find the b sub n's is we say, what should I multiply the sine of n pi x over L by so that almost all of these terms are gone, but I don't want them all to be gone completely. I want this times something else. I want to be able to integrate that and still have the b sub n that's left. Well, if I take a sine function and I multiply it by a different sine function, I'm going to get 0 most of the time, except for when those two angles are the same. So because this is multiplied by a sine, in order to solve for the b sub n, we multiply by the sine of m pi x over L on both sides. And then because of these identities, most of those expressions in our equation will be 0, and we'll be able to solve for b sub m, which we can quickly change to b sub n. So I had f of x, I multiplied by the sine function and I integrated, equals my constant. I multiply by the sine function and I integrate. I've got a sub n times cosine of n pi x over L, and we're taking that sum as n goes from 1 to infinity, multiply by the sine function and integrate. Since this is a function of x, I need that inside. And then I had the sum as n goes from 1 to infinity of b sub n times this sine function. I multiply by the other sine function, and then I integrate from negative L to L. So as we said before, I've got an identity for this. I justified it geometrically. That integral turns out to be 0. With sine and cosine multiplying each other, that integral turns out to be 0. And we could verify that using the methods from the trigonometric integrals section if we wanted to. And then for this last one, I've got 2 sine functions. We say that's going to be 0 most of the time. But when n and m are equal, so these sine functions are the same, turns out we're going to get L. So we're taking an infinite sum, n goes from 1 to infinity, but almost all of those b sub n's are multiplied by 0, except for b sub m. B sub m is multiplied by L. That means b sub n, I'll just change from m to n. Well, let's write it in terms of m first. We have b sub m times L from the right-hand side equals the integral from negative L to L of f times sine of m pi x over L. And if we want to switch to n, as we often do, we'll just let m equals n. It's a dummy variable that's totally allowed, and then we divide by L there. And we get this. So we have this formula, and all of those were derived from first principles. Okay. So that's how we find the formulas for the coefficients of the full Fourier series for a particular function f. But now let's say we're interested in a cosine series. Well, the question is, how do those formulas change when f is an even function? Remember, cosine is an even function. So if f is an even function, we should have a lot of simplifications. So let's go down here. When f is an even function, recall this fact. I'll put it over here with my list of identities. Say facts. If f is even, the integral from negative L to L of f of x turns out to be 2 times the integral from 0 to L of f. And remember why that's true. We just got y equals x squared there as an example of my even function. If I'm integrating an even function over a symmetric interval, well, the area on the, or to the right of the y-axis is going to be equal to the area to the left. Or you can think of it as net area, area above the y, or above the x-axis minus area below. Because the function is even, you're going to have the same net area on the right that you would have on the left. So you could just find the area on the right, on the interval from 0 to L, and then double it, and that will work. So we know that's true. Other things that we talked about before are that if you take an even function and an even function, and you multiply them together, you get an even function. If you take an odd function and an odd function and multiply them together, you get an even function. And an odd function times an even function, or an even function times an odd function. Of course, we can multiply in any order we want. So we're thinking of real valued functions here. That's going to be odd. Okay, so if our function f is even, that means this integral from negative L to L can be simplified using this identity. I can replace this with 2 times the integral from 0 to L of my function f. So if f is even, or when f is an even function, we'll have a sub 0 equals 2 over L. That 1 over L times the 2 gives me the 2 over L, times the integral from 0 to L of f. We're interested in when f is even because we're trying to come up with that Fourier cosine series. We're just seeing how these formulas simplify if f happens to be even. Okay, so now let's look at the a sub n's and see how those simplify if f happens to be even. Well, if f is even, this is an even function times an even function. So even times an even is an even function. That means this integral from negative L to L of this is the same as 2 times the integral of the same function from 0 to L. And of course, f depends on x. So if f is even, a sub n becomes 2 times that 1 over L, which is 2 over L, times the integral from 0 to L of f of x times cosine of n pi x over L. Okay. Now for this last one, notice we've got an odd function, or excuse me, an even function times an odd function. And an even function times an odd function is an odd function. Now I didn't write that on the other side, but here's another fact. Let's say that g is an odd function. If g is an odd function, then the integral from negative L to L of g of x is equal to 0. And just to give us sort of a way to visualize that, let's look at y equals x cubed. If I take the area on the left and the area on the right, those areas are the same, but they're counted with opposite signs because one is above the x-axis while the other is below. So that area will always be matched by that area and they'll cancel. So the area over here, or the integral from 0 to L of g of x, is going to be the opposite of the integral from negative L to 0. So if this area was, say, 2, that area would be 2 as well, but be counted as negative. The integral from negative L to 0 would be negative 2, and the integral from 0 to L would be 2. And so we'd have the 2 plus the negative 2 gives us 0. Or this area and that area match, so this area minus that area is 0. So if g is odd, we get this. So this is the integral from negative L to L of an odd function. That means all of that is 0. Okay, so that makes sense. That means our b sub n's are 0 if f is even. So this here, combined with what we talked about in the last video, gives us formulas and methods for even and odd extensions of f. So let's say we're given f, and rather than having f defined on the interval from negative L to L, let's say we have f defined on the interval from 0 to L. Let's say it just looks like this. If I wanted to create an even function based on this, remember what we say about even functions. F of x, that's the y value, x units from the origin on the right. And f of x, f negative x, that's the y value, x units from the origin on the left. If you go the same distance, you're gonna have the same y value. So what we would do is we take this guy, this little line segment, and we sort of reflect it. There's symmetry about the y-axis here. That would be the even extension of f. So now we have an even function that was defined using the function f, or we could create an odd function defined using that function f. For the odd extension of f of x and f of negative x aren't the same. They're opposites of each other. So I'll multiply one of them by negative 1 and set them equal to each other. That means when this one is equal to L, the other side, on the other side, our function will be equal to negative L. So what we'd see is something like this. We have symmetry about the origin here. Okay. Now, in the last video, we talked about what happens when you have an odd extension of f. And of course, we create a periodic extension from this. So we would just draw this over and over again so that we'd have the periodic extension of the odd extension. We said in that case, if we have an odd function or an odd extension of that function, it makes sense to construct a Fourier sine series. And it has this form. Now, if we have an even function, we said it makes sense to construct a Fourier cosine series. And that's just going to look like our Fourier series, but all those b sub n's are 0. So we just end up with 1/2 a sub n plus the sum as n goes from 1 to infinity of a sub n times cosine of n pi x over L. And of course, we're not just looking at the even extension, but we're looking at a periodic extension of the even extension here. And we're saying that under certain conditions on F, this would be equal to this series. And here we take a periodic extension of the odd extension. And after we do that, we said it makes sense to talk about a sine series for that function. And under certain conditions, these guys are equal to each other. So that's sort of a recap of what we did last time. Since cosine is an odd function, it makes sense that it would go with the even extension. Excuse me, cosine is an even function. So it makes sense it would go with the even extension. And since sine is an odd function, it makes sense that it would go with the odd extension. Okay, so that's the idea. Let's do an example now. So our problem statement says, construct the Fourier cosine series for F, discuss the convergence of the series on the interval from 0 to L where F is defined, and sketch the functions to which the series converges pointwise on the interval from -3L to 3L. We're using this piecewise function F. We see that it's defined from 0 to 1 and then from 1 to 2. So the entire function is defined on the interval from 1 to 2. So that tells us that L is equal to 2. And the first thing that I would recommend is that you sketch this. So on the interval from 0 to 1, we get 0 when x is 0, we get 1 when x is 1, and we just got the line y equals x there, that little line segment. And then on the interval from 1 to 2, our function value is -2, and we're not including that endpoint at x equals 1. So we'll have an open circle there. And we have this. So that's y equals f of x. Now, since we're interested in the cosine series, and cosine is an even function, we want to construct the even extension of f. So basically, we're taking this function on the interval from from 0 to 2, and we're extending it to the interval from -2 to 2. So we're just going to use reflections to do that. On the interval from 0 to 1, we had this. On the interval from 1 to 2, we had this. Now for an even extension, remember what happens with an even extension. You look at the y values, x units to the right, and then you look at the y values, x units to the left of the origin, and you want those to be equal to each other. So basically what we're going to see is a reflection of this function over here. Okay, so this is an even extension of f on the interval. This is f on the interval from 0 to 2. That's 0 to L in general. This is on the interval from -2 to 2, or -L to L in general. So that's our even extension. And now we might want a periodic extension of that even extension. Now this function is very similar to the function that our Fourier cosine series will converge to. And we were supposed to graph this, or we were asked to graph this on the interval from -3L to 3L. Since L is 2, we're going to graph from -6 to 6. Now, technically, this is not the function that the series will converge to, but it's very closely related to the function that the series will converge to. Okay, so first we'll draw f on the interval from -2 to 2, but leaving off that point at -2. So that we actually define a function. So that's our pattern, and we want to repeat that 3 times. So if I were to take this and pick it up and draw it again over here, I would see this. There would be an open circle, and then over here to another open circle. Then from 3 to 5, I would see that V shape again. And then from 5 to 6, I would have that open circle followed by the closed circle. So that's 1 period, that's 2 periods. And then over here, we're going to see something very similar. So from here to here, I would have that. And then from -5 to -3, we'll see that V shape. And then from -6 to -5, we'll see this. Okay, so that is the periodic extension of the even extension of f on the interval from -6 to 6. Now, clearly, this is a function that is periodic with period 2L, or in this case, period 4, because it repeats itself every 4 units. There's 1 period, there's another period, there's another period. Since it's an even function, it makes sense to construct a cosine series. Now, if we construct that cosine series from first principles, this is what we get. So we will initially assume that f of x is equal to its cosine series. And of course, we're only saying that that's equal where the periodic extension is continuous. So we're just formally treating this as if they're equal. It's n pi x over L, and L equals 2. So we'll have n pi x over 2 there. To find a sub 0, we treat these as we treat f as equal to its cosine series, and we integrate from -L to L. So we have the integral from -L to L of f of x with respect to x equals 1/2 a0. And we'll integrate that from -L to L with respect to x, plus the sum as n goes from 1 to infinity of a sub n times cosine of n pi x over L, where L equals 2. We integrate that from negative L to L. From before, we know that this simplifies to 0. And if we integrate this constant with respect to x and substitute x equals L and x equals negative L and simplify, this piece ends up being just a naught times L. You can confirm if you want to. So a naught is equal to 1 over L times the integral from negative L to L of f of x. Now we're interested in the periodic extension of the even extension of f. So that means this integral from negative L to L, the area under this curve, or the net area, that area minus that area, well, it's going to be the same on both sides. So we can just take the integral from 0 to 2 and double it. I've got these L's everywhere, but these should be 2's. Integrate from negative 2 to 2. Substitute in L equals 2. So I have 1/2, that's from my 1 over L. And then we double it. And then we say, rather than integrating from negative 2 to 2, I'm just going to integrate from 0 to 2 and then double it. Because f is an even function, or because we're interested in the periodic extension of the even extension of f. And so that's pretty straightforward. F is a piecewise function. It's defined to be x on the interval from 0 to 1. And it's defined to be negative 2 on the interval from 1 to 2. And we can just evaluate those for this first one. Use the power rule, add 1 to the exponent, divide by the new exponent, substitute in 1 and 0 and subtract. Over here, the antiderivative of a constant is that constant times your variable. Substitute in 1 and 2 and subtract. And what you get is 1/2 minus 0 minus 2 times 2 minus 1. So we have 1/2 minus 2, which is negative 3/2. And if you're saying to yourself, is that right? Let's look at this area over here. I've got 1/2 is this area. And then we're going to subtract this area, which is 2. 1/2 minus 2 is that negative 3/2. And then we would double it. So we get negative 3 for the integral from negative 2 to 2 of f of x. But then the formula says take 1 over L times that. That's your a naught. 1 over, or an L in this case is 2. So we get negative 3 times the 1/2, which is the negative 3 over 2. Or you just get the area for one side there, same thing. All right, so that's our a naught. And now we want to find the a sub n. To get rid of these, to get rid of almost all of these, because we've got infinitely many of them, we multiply by cosine of m pi x over 2. Multiply everything in this equation by cosine of m pi x over 2. And then use those identities that we used before. So I've got f of x here, and I'm multiplying by cosine. And we integrate from negative L to L. And that's equal to 1/2 of a naught times cosine again. And we integrate from negative L to L. And then we have the sum as n goes from 1 to infinity of a sub n times cosine of n pi x over L, and L is 2. So we're going to multiply this one by cosine of m pi x over 2. And we integrate from negative L to L, which in this case is negative 2 to 2. All right, this is a constant times the integral of that cosine function, which we know to be 0. And then this is 0 most of the time, whenever the angles are different. But when the angles are the same, we get L, which happens to be 2 in this case. And then over here, we've got that integral. So this will be a sub n times 0 almost all the time, except when n is equal to m. When n is equal to m, we'll have a sub m times 2. I'll have 2 times a sub m equals the integral, and L is equal to 2. So it's the integral from -2 to 2 of f times our cosine function. And then usually we switch from m back to n. And we divide by that L over there. In this case, L is 2. To get this. Now this is the product of an even function and an even function. An even function times an even function is an even function. And for an even function, this integral on the interval from -a to a is the same as twice the integral from 0 to a, or twice the integral from 0 to 2 in our case. So that integral is equal to that. And of course, when we multiply by the 1/2, the 2 and the 1/2 reduce, and we just have this. Now in the interval from 0 to 1, f of x is equal to x. On the interval from 1 to 2, f is equal to -2. So we're just substituting x in for this interval, and we're substituting -2 in for the next interval. And then we just evaluate these. Since I've got a polynomial times a cosine function, I will use tabular integration by parts. So of cosine of n pi x over 2 here. So we're ignoring the dx for right now, so we write that there. And then we differentiate in this column. Derivative of x is 1, derivative of 1 is 0. Then over here, we take the antiderivative of cosine of n pi x over 2. Antiderivative of cosine is sine. But since we have something multiplying the x inside, we've got to divide by that. Dividing by n pi over 2 is the same as multiplying by 2 over n pi. The antiderivative of sine is negative cosine. And then we will have to divide by that n pi over 2 again. So that means we're just multiplying by the reciprocal. We end up with 4 over n squared pi squared. Don't forget that plus minus plus when we use tabular. So we'll have this times this. And then we'll add -1 times this times this. -1 times that negative is going to give us a positive. Evaluate from 0 to 1. Now over here, we'll bring the -2 down, and we'll take the antiderivative of cosine. Let's just sine of n pi x over 2. And if you've got a constant multiplying your x inside, you've got to divide by that constant. So that's going to be multiplying by the reciprocal of that fraction. So we multiply by 2 over n pi. And we evaluate this expression from 1 to 2. Okay, so at x equals 1, we get 2 over n pi times sine of n pi over 2. And then over here, we've got 4 over n squared pi squared times cosine of n pi over 2. That's when we substitute x equals 1. When we substitute x equals 0, we've got 0 times something, which is clearly 0. And then we've got cosine of 0 over here. Cosine of 0 is 1. So we'll just have a 0 plus this times 1. So we're subtracting that expression. So we're subtracting 4 over n squared pi squared. Then if we evaluate this at x equals 2, we've got sine of n pi. And if we evaluate this expression at x equals 1 and subtract, we're subtracting a negative 4 over n pi. So it's going to be positive 4 over n pi. And then we've got a sine of n pi over 2 there. And then we simplify wherever we can. I've got 2 over n pi times this sine function, and then 4 of those over here. So that means I've got a total of 6 of those. And then I've got one of these cosine functions. So I've taken care of this guy and this guy and this guy. And next we have that one. Now remember, n is an integer. So if n is an integer, we're going to use n equals 1, 2, or it's actually a positive integer. N equals 1, 2, 3, 4, and so on. So we'll have pi over 2, then we'll have pi, then we'll have 3 pi over 2, then we'll have 4 pi over 2, which is 2 pi, and so on. So this sine function is going to start at 1, and then it'll be 0, then it'll be negative 1, then it'll be 0 again, then it'll be 1, 0, negative 1, 0, and it'll just keep repeating. This does the same thing, but it's not really easy to simplify in terms of, say, negative 1 to the n or anything like that. But here, when I have sine of n pi, that's like sine of pi, sine of 2 pi, sine of 3 pi. We know that our sine function looks like this. Not to scale clearly, I didn't do a very good job with symmetry there either. But that function crosses the x-axis at all the multiples of pi. So this will always be 0, and that's gone. So that's our a sub n. So that is enough for us to say that the cosine series for our function is 1/2 of a sub 0 plus the sum as n goes from 1 to infinity of a sub n, which is all of that, times cosine of n pi x over L, where L equals 2. So I will just rewrite all of this right here. Usually look for some factor that they all have in common. Well, you can take out a 2 over n pi from everything if you want to. Oops. And 2 over n pi, if I factor that out from here, I'll have a 3. If I factor that out from here, I'll have another one of those. And if I factor that out from this last one, I have that. And my a sub 0, or a naught, if you prefer, was negative 3 over 2. So the Fourier cosine series for f is given by this. And sometimes that converges to f. The question is, well, in general, what does it converge to? Well, remember what we said earlier when we talked about convergence in that first video. The function, it says functions, it should just say function. The function to which the series converges is very closely related to this periodic extension. It's going to be equal to the function, or to this periodic extension, whenever the periodic extension is continuous. So we can see from this image that the periodic extension is continuous from -3 to -1, and then it's continuous from -1 to 1, and then it's continuous from 1 to 3, and so on. But there are jump discontinuities for this. So the series is not going to converge to this function. The series is going to converge to this function. It's going to be exactly the same as this guy, where the function is continuous. Except it's going to have open circles here. And then at the jump discontinuity, the series will converge to half of that value, or excuse me, half of the sum of these two values. The limit as x approaches -1 from the left is -2. The limit as x approaches -1 from the right is +1. The average of -2 and +1 just comes from adding those and dividing by 2. So we're going to get -1 divided by 2 is -1/2. So the series is actually going to converge to that point and that point. Now we're usually only interested in where the series converges on the interval from 0 to L. So in our case, on the interval from 0 to 2. So the series converges to this. It's going to be f, where the function was continuous, or where the periodic extension was continuous. So it'll be f of x, which is equal to x on the interval from 0 to 1, including 0 because the periodic extension is continuous there. At 1, we have the average of the limit from the left and the limit from the right. The average of those two is 1/2. And then on the interval from 1 to 2, we get a y value of -2. And the periodic extension is continuous at 2. So we can use an equal sign here. Less than or equal to. And if we wanted to draw the periodic extension of the even extension of f and graph it, we would be graphing pretty much the same thing that we graphed here. The only difference is that at these endpoints, and actually, I think this should be an open circle as well, not a closed circle. At all of the jump discontinuities, our series would converge to that average of the limiting value from the left and the right of the jump discontinuity. That's it for our discussion of Fourier cosine series. Next time, we'll talk about the Sturm-Liouville problems, which occur a lot when solving other types of problems, both in differential equations and in physics. So it's tons of fun.